all of you to be ready with a note and pen. Right. So, good afternoon, everyone. Once again, welcome to another online session of Principles of Communication System. So now we are into third module, and we are discussing about noise in continuous modulation system. Right. So we have discussed about different types of noise, and in last class, we have studied about noise in double sideband suppressed carrier system, and we found the figure of merit of DSB SC. We found it to be equal to 1. So that was the result which we got. So today what we will do is we'll study noise in AM system. Right, noise in AM system. When I say noise in AM system, it means it is actually what standard AM with carrier, right? Standard AM, right? Or the question can be about AM using envelope detector, right? AM using envelope detector, right? Or with carrier, right? The topic can be anything, right? So for all these things, the following discussion is what you have to consider. So for as just like any other system, right? So when we are considering the noise, when we are about to analyze the noise in AM system, first we should have a system model, right? So that system model is nothing but what? So we have AM signal, so we'll represent it as S of t, right? We have AM signal. So then we have, right, additive white Gaussian noise, right? Noise W of t contaminating our AM signal, right? So this we will pass through a band pass filter. We will pass it through a band pass filter, right? So this band pass filter will have some characteristics which will allow the S of t completely, right? It will be centered at FC, and this bandwidth is exactly same as that of S of t, so that it will allow S of t, right? So we are passing it through a band pass filter. Then we are passing it through an envelope detector. In last case, for DSBAC, we have considered a coherent detector. So in this case, we are considering envelope detector. So please do take down along with me, right? In between, right, I will be solving a problem that I'll ask any one of you to solve. I'll ask any one of you to share the screen randomly, and I'll ask you to solve it. If you are not able to solve, right, then we see, right? Yeah, okay. So we are getting output signal y of t here, right? So this is our S of t. This is our x of t. Band pass filter output is x of t, right? This x of t is equal to what? Will be equal to S of t plus n of t, where S of t as such will be available at the output of band pass filter, where this n of t is actually what? The band pass filter W of t, right? W of t after band pass filtering, we'll get n of t. This is a narrow band noise. This is a narrow band noise, right? We have seen it can be represented as in phase component times cos 2 pi fct minus quadrature phase component. This is the system model what we have, right? So what do you mean by analyzing noise in AM system, right? We have to find out the figure of merit, that is SNR output divided by SNR channel, right? So that is what we have to find out. So we'll try and find out that, right? So we'll move on, right? So our S of t, before that, we'll assume the message, right? We'll assume the message is M of t, right? M of t, and it has a spectrum like this. Message has a spectrum like this. This is M of f, right? It is 0 to W and minus W. So message has a spectrum like this, which means it has maximum frequency content equal to W, right? And the average power of message power of m of t, we are assuming it to be equal to capital P watts. So we are assuming initially itself the power is equal to capital P watts, right? Then what we have is, we have this S of t, right? What is the time domain expression for standard AM? It is AC into 1 plus Ka m of t cos 2 pi FCT. This is the time domain expression for standard AM, right? So its spectrum will be something like this, right? You all know what does how the spectrum will look like, right? Again, its spectrum will be maybe right. So just excuse me. We'll assume the spectrum of message. Right, we won't consider it as actually what a perfect baseband signal. So instead of that, we'll consider the spectrum to be something like this, right? Sorry, right? This is how we have. It's an arbitrary spectrum of this shape, right? That's what we used to have, right? So the spectrum of S of t, it will be something like this. Spectrum of S of t will be something like this, and it will have carrier also, right? In this case, it will have carrier also. So it is FC, FC plus W, FC minus W, and here again on negative side, minus FC plus W, and minus FC minus W. So this is the spectrum of S of t. S of f will be like this. So you can see the bandwidth will be equal to 2W. The message bandwidth is equal to actually what? Message bandwidth is W, right? And S of t, the bandwidth is 2W, twice the. We have already studied this, right? So now, if this is S of t, what will be average power in S of t? Maybe we'll find out that. Initially, what we need to find is SNR, channel SNR, right? We need to find channel SNR, that is SNR C. It is nothing but the channel SNR. It is defined as ratio of average power of modulated signal divided by the average power of noise, average power of noise within message bandwidth, right? So please do remember this, right? Please do remember. So this is the definition of channel SNR, channel signal to noise ratio. It is defined as a ratio of average power of modulated signal to average power of noise within message bandwidth. So this is average power of noise within message bandwidth, right? So that's why in the case of DHB-AC, when we were considering the noise power at the in for SNRC, we considered it equal to NOW. But while we were considering at the output, we considered 2 NOW. I hope you remember that. I've asked you to. I've stressed on that point, right? Maybe that is the only place where you may find it confusing. That is because, right, SNR, channel SNR is defined like this: average power of modulated signal divided by average power of noise within message bandwidth. For you to remember this, right, the measurement of channel SNR, right? I'll draw a diagram, right? I'll draw a diagram so that you'll be able to remember. So here, suppose we are giving message signal, right? Message signal with same power as modulating wave, right? With same power as S of t. So if you are giving this, and we have noise W of t, right? Noise W of t, and if you are passing it through a low pass filter, this is the equivalent model, okay, to find SNRC, right? Low pass filter of bandwidth equal to W, right? Low pass filter of bandwidth equal to W. If you are getting output, right? If you are getting output, so the signal to noise ratio here, right? The SNR measured at output of this particular scheme, that will be SNRC, right? So please keep in mind, right? Please note it down. Right. So what we are doing is we are assuming message signal with same power as S of t, same power as modulated signal, that is contaminated with noise. Right. That is passed through an LPF. LPF, its transfer characteristics will be like the 0 to W or minus W to W. Right. So what will be the noise output in this case? Noise output in this case is noise has a spectral density like this. It is n0 by 2 for all values, right? So now S n of f in this case, it will be something like this. n0 by 2 from minus W to W, right? n0 by 2 from minus W to W. So noise power, right? Noise power will be Pn in this case will be integral minus W to W. I'll write n0 by 2, right? df, right? So this will be, this df will be what? If you integrate this, you will get n0 by 2 times 2W. This will be equal to n0 W. So the noise power or the denominator, right? This denominator, right, is this n0 W. The denominator is n0 W. So please do keep in mind, right? So, but while evaluating noise power at the output, we will be considering a band pass filter, right? At that time, we'll be considering a band pass filter. So we'll have a total band of actually what? This will be, there is a 2W here and a 2W here. So it will be 4W times n0 by 2, right? So I'll discuss that here. But this aspect, please do keep in mind. Like some of you have asked out, right? Some of you have asked out in this aspect why it is only n0W, not n02W. That is because of this definition. This is how it is defined. Why? Because when we are comparing different modulation schemes can have different bandwidths, right? So different bandwidth. So when we have to compare the input side, what we are taking, it should be like similar, right? It should be comparable. So that's why we are considering average noise power within a message bandwidth. If you are considering noise power within modulated signal bandwidth, the modulated signal bandwidth will be different for different modulation schemes, right? So that's why we are defining channel SNR or input SNR like this. So please do keep in mind. Right. So now we'll find the power in S of t. Right. So S of t, again I'll write S of t is AC into 1 plus Ka m of t. All of you please take down, right, m of t cos 2 pi fct, right? Or this is equal to AC cos 2 pi fct, AC cos 2 pi fct plus AC Ka m of t cos 2 pi fct, right? So what is the power in AC cos 2 pi fct? That will be, average power will be equal to AC square by 2 plus, so here we have actually what, one AC cos 2 pi fct, right? One AC cos 2 pi fct will be there, its power will be equal to AC square by 2, that is AC square by 2. Then we have a Ka. So whenever we have Ka, a constant, we should take square of it while finding average power. And m of t, we know power of m of t is equal to P. Power of m of t, we have already defined, it is equal to P, right? So the average power, right? So I'll write here average power in S of t. This is the numerator of channel SNR, that is equal to AC square plus AC square by 2 Ka square P. So we can write it as AC square into 1 plus Ka square P all divided by 2, right? So, and average power of noise within message bandwidth, this is equal to, just now we found out it is equal to n0W, right? So what is the SNRC? SNRC, channel SNR is equal to AC square into 1 plus Ka square P. This 2 will come to denominator times 2 n0 W. So this is channel SNR in the case of standard AM. This is the channel SNR in the case of standard AM. So we'll keep it here. Maybe I'll call it equation number 1. Right. So once again, we'll just remember what our system model was. We had, right, we had W of t getting added with S of t. This is being passed through a band pass filter. Right. So here we'll get X of t. Right. This X of t is then passed through an envelope detector. Is then passed through an envelope detector. Right. So that is what, and that is the output envelope detector. Then here we are getting output, that is Y of t. Right. So now what is this X of t? Right. X of t is equal to S of t plus N of t. We know what is S of t, and N of t we can represent it in canonical form as Ni of t cos 2 pi fct minus Nq of t. T should be there, and Q of t sine 2 pi fct. So we can use it here. So this is equal to S of t. I can write AC into 1 plus Ka m of t cos 2 pi fct plus N of t is Ni of t cos 2 pi fct, right, minus Nq of t sine 2 pi fct, right. So this is X of t. This is again X of t. This X of t is passed through an envelope detector. So what an envelope detector does is, right, it detects only the envelope. It detects only the envelope in the sense how the amplitude variation, right. So normally an envelope of a signal can be obtained easily by what, representing it in polar form. If you represent the signal in polar form or in like in phasor form, the magnitude part will be its envelope, right. So right, so that will be its envelope. So we'll try to find out what is the envelope of X of t, right. So maybe for that, this representing it in phasor form is actually what is equivalent to what representing it in canonical form. Canonical form means we can represent it as in phase component times cos 2 pi fct minus quadrature phase component times sine 2 pi fct, right. But where this in phase component will be the real part. If you are representing it in complex form, in phase component will be real part and quadrature phase component will be imaginary part. So what I'm going to do is I'm going to represent it in canonical form. Canonical form means something into cos 2 pi fct minus something into sine 2 pi fct. Right. I think someone is trying to join in. Right. I hope all of you are noting it down. Right. So so I can collect all cos 2 pi fct terms. So cos 2 pi fct is AC, 1 plus km of t is there, and then Ni of t is there. That will be the in phase part here. So AC into 1 plus Kam of t, right, plus Ni of t. This entire thing into cos 2 pi fct minus Ni of t sine 2 pi fct. Right. So this is X of t. So this is in, I'll write this is in canonical form. This is in canonical form, which means something into cos 2 pi fct minus something into sine 2 pi fct. So if you have represented a bandpass signal in its canonical form, you can find its envelope. You can find its envelope, its complex envelope as, right, root of in phase component square plus quadrature phase component. It should be NQ. Sorry, I have written it by mistake as Ni. Right. So here it should have been NQ. So its magnitude. So and Y of t is nothing but what, Y of t is nothing but envelope of X of t. Envelope of X of t. So envelope of X of t can be found out as actually what, square root of a square plus b square, where a will be the in phase component and b will be the quadratic phase component. So here this entire thing is a and this entire thing is b, right? So we can find envelope like that. So the envelope here would be, so the envelope, that is y of t, is equal to, instead of square root, I am writing it actually what, to the power half, right? So we can write it as this ac square, or maybe ac plus ac km of t I can write, ac plus ac ka m of t, ac plus ac km of t plus ni of t plus ni of t. This is in phase component, so I should put it inside the bracket and square, plus nq square, I should write nq square of t, this entire thing to the power half, under root of this. And it's actually what this is representing it in canonical form is equivalent to what representing it in like Cartesian form, right? Anything. So its magnitude or envelope can be found out as root of a square plus b square. So this is the envelope. So this is what we'll get at the output, but you can see this is a bit a complicated expression, right? Maybe I can try and represent it as say a phasor, right? If I try and represent it using phasor, then that would be easier for you to visualize. So in phase component, so this, suppose this is our complex plane, this is my complex plane, right? I'll take another ink. Yeah, right. In phase component is this much, ac plus ac km of t times na of t, or ac into 1 plus km of t. So say this is this much, let us assume it is ac into 1 plus ka m of t. To this we have in phase component of noise, right? In phase component means ni of t also will be having same phase angle. Ni of t also will be having same phase angle, that is ni of t. Then we are adding quadrature phase component. So quadrature phase component means nq of t will be 90 degree to it, right? This will be nothing but what, nq of t, right? So when you are adding these things together, what we'll get is, right, so the resultant of ni of t and nq of t will be something like this, right? And when you're adding this, I'll use greening to draw the resultant, right? So this is how the resultant will look like, right? This is how the resultant y of t will look like. So you can see here this ac into 1 plus km of t, that is actually what, very large compared to our noise, right? So the resultant y of t and ac into 1 plus km of t, right, both, right? So I can write y of t is almost equal to what can be approximated as ac plus ac km of t, ac plus ac km of t, maybe plus ni of t, right? As is nq of t, the magnitude of nq of t is much less compared to what, this entire thing, right? nq of t is much less compared to this entire term. What we can do is, this y of t can be approximated as ac into 1 plus km of t plus ni of t. Or in other words, if you see, if the angle here, it is theta, right? So this ac into 1 plus km of t plus ni of t, that is, it is nothing but what, the horizontal projection of this particular phasor, right? Or the real part of this particular phasor, right? So that you can see, as this theta is very small, right, the real part is nothing but what, y of t cos theta, right? As theta is very small, cos theta will be almost equal to 1. So this y of t can be approximated as the real part. We can neglect the imaginary part. So that is what we are doing now, right? So that is the, I'll repeat, right? That's why I've represented it as phasor. That is, as carrier amplitude is, right, carrier amplitude is much greater compared to what, nq of t, or carrier amplitude is much greater compared to noise, this NQ of t can be neglected, right? So even though it's phasor, so how actually it happens, that's what I've demonstrated, right? So we can approximate this y of t to be, y of t can be approximated as AC plus AC Ka m of t, AC K m of t plus Ni of t, AC plus AC K m of t plus Ni of t. This y of t can be approximated like this. Now what we need to do is, right, we need to analyze this. So we have an AC term. This is due to the carrier which is not suppressed. We are transmitting carrier along with the standard AM in order to reduce the simplicity, as so that we can use the envelope detector, right? In order to reduce the complexity of the transmitter and receiver system, right? We are transmitting carrier. So this AC, it is like a DC offset, right? It is like a DC offset, DC shift. It as such does not carry any information, right? If AC is right, so it won't actually what affect the envelope, right? The envelope, if it is something like this, and this AC term will either actually what shift it up or pull it down. It is like a DC offset. So this as such does not carry any information. This AC K m of t, this is the term with m of t. This is the term which contains m of t, and Ni of t, it is the in phase noise term. So N of t is the W of t filtered by a band pass filter. It is the in phase component what we have. So just like what we have seen in DSBSC noise analysis, the in phase component is appearing additively with the message, but we have an additional AC here. This AC, right, it doesn't have any other any information, like it can't give any information. It will either actually what clamp the envelope up or down, that's it. So this AC we won't be considering while evaluating, right, the message or the output power. We don't have to consider this AC. Somehow we have to suppress. Why? Because it's a DC shift up or down, so we are not interested in that. Our interest is in envelope, so we are not considering AC. So while evaluating the message power at the output, we have to consider only this term, right? And while evaluating noise power, we have to consider this term. So that's what we have to do, right? So now we have to find SNR at the output, right? To find SNR at the output, right? So message power in Y of t, right? Average message power in Y of t. This is actually what this Y of t, it is an approximation. It will hold good only when carrier amplitude is much greater compared to noise, right? This approximation will hold good only when carrier amplitude is much greater compared to noise. Please do keep that in mind, or else it is true if and only if carrier to noise ratio, I'll use a new term, carrier to noise ratio is much greater compared to 1, right? Carrier to noise ratio is much greater. Carrier power to noise power, that ratio is much greater compared to 1. Then only this will hold good, right? And one more thing is that if we have to use an envelope detector, we know the modulation factor should be less than 100%. Mu should be less than or equal to 1, or Ka should be adjusted in such a way that there is no phase distortion, right? So that you already know, right? So those two conditions should be met if this approximation has to be true, right? So now we have to find what is the average message power in Y of t. That is actually what power of AC Ka m of t. Now can anyone tell me what is the power in AC Ka m of t? We have evaluated. So we have AC a constant, Ka a constant, and m of t, right? It's a message signal. So what will be average power in this? It will be a numerator of output SNR. So I want all of you to please type it in chat window. What is the average power within that? Yeah, I need all of you to type in. All of you should respond. Right. It should not be right, simply a wastage of time. So please, I'm expecting all of you are doing this derivation along with me. Right. So all of you should be in a position to type it down. Yeah, I'll give, say, 1 minute time. Yeah, please. I can't see any answer here. Yeah, at least one answer I should get. AC square Ka square P by 2. Why, Pritish, there is a P by 2? Why do we need that P by 2? AC and Ka you can treat as DC, right? So AC is a constant, so the average power will be power delivered to 1 ohm resistor will be proportional to square of it, right? K again it will be square of it, so AC square Ka square, and we have M of T, right? M of T is a message signal. We already know what is the power, average power delivered by M of T to a 1 ohm resistor. That will be equal to P. So it will be AC square Ka square P. It will be AC square Ka square P, right? Not AC square Ka square P by 2. Had it been AC square AC K M of T times cos 2 pi FCT, then the average power delivered by AC cos 2 pi FCT to 1 ohm resistor would have been AC square by 2. But in this case, this is AC square Ka square P, right? So Pritish has given an answer, right? Thank you. Yeah. So then we'll move on. So this is the numerator. So now noise power average noise power at output, average noise power at output. So just I'll just revise again. So we have this noise with power spectral density Sn of f is equal to n naught by 2 for all frequencies. This, right, this as well as this, be n of t or ni of t or nq of t, right, it will have same spectral characteristics, right? So the power density, you can assume it to be, it will be same, right? Once it is passed through a band pass filter, what we'll get is, we'll get output spectral power spectral density like this. So this will be, say, fc plus w, fc minus w, and this is n naught by 2, right? So on either side, so the power, right, power out will be, so this is Sn out of f, right? Sn out of f, this will be what? It will be area under this curve. What will be area under this curve? So we have both positive and negative. So on positive side, the area will be n naught by 2. So it's nothing but what? Area of a rectangle. It is actually what? Length into breadth. So this is 2w, this length is 2w, and this height is n naught by 2. So that is n naught by 2 times 2w. So that will be n naught w. And here again we have 2w and n naught by 2. Right. The area is positive. Right. Area is positive in both the cases. So it will be n naught w plus n naught w. It will be twice n naught sorry w, right? So the average noise power at output, it will be equal to twice n naught w, right? Now we can write the output SNR, right? SNR out, it will be equal to AC square Ka square P divided by 2 N naught W. So this is output SNR, right? This is output SNR. Now, just remember what was input SNR, SNR or channel SNR. What was SNR channel? Please tell me. That I've already discussed. Right. So please type in what is channel SNR. That we already found out, and I am expecting you to have taken it down. Right. So what is channel SNR, SNRC? Please, some of you can unmute and tell, or you can type it in, not a problem. So Srisha's AC 1 plus map K square P by 2 NOW, right? Okay, thank you. Right, so or else we'll just cross verify what is the answer, right? The AC square 1 plus Ka square P divided by 2 NOW, that is channel SNR, right? So I'll once again take it down here. Channel SNR is AC square 1 plus Ka square P divided by 2 N naught W. So this is channel SNR, and what we have on left hand side is the output SNR. So the figure of merit, right? Figure of merit of AM, standard AM, it is equal to SNR at the output divided by SNR of the channel. So that is this 2 NOW and 2 NOW will get cancelled. So what we have is AC square again will get cancelled. AC square also, but I'll write, right? Okay, or else I need not write. So the AC square and AC square will get cancelled. 2 NOW and 2 NOW will get cancelled. So what we have is this Ka square P divided by 1 plus Ka square P, right? So I'll rewrite it. So figure of merit of AM, that is AM with envelope detector or standard AM, it is equal to Ka square P divided by 1 plus Ka square P, where P is the message signal and Ka is the amplitude sensitivity, right? So this particular figure of merit value or this fraction, right? I'll give three options. It will be always equal to 1, B, it will be always greater than 1, C, it will be always less than 1, which is true. K square P divided by 1 plus K square P, right? Which one is true? It will be, it will be always equal to 1, or it will be always greater than 1, or it will be always less than 1, which is true. You can type in. It will be always less than 1. Why? Because it's right less than or equal to 1. If P is equal to 0, or if P is equal to 0, right, then what will happen is, no, even then, right, it will always be, say, less than 1. It will always be less than 1, right, compared to what was the figure of merit of DSBSC, FOM of DSBSC, it was equal to 1, always equal to 1, but here figure of merit of standard AM is always less than 1, right, which means the noise performance of standard AM is less than that of or worse than that of actually what DSBSC. That is because for the sake of simplicity of the transmitter and receiver, we are transmitting redundant power which does not carry an information. This is carrier power, right, even though it can help reduce the complexity of transmitter and receiver, right, it's actually what a burden, overburden. It's an additional power which, right, which does not carry any information, right? So when it comes to what noise performance, that is right affecting it adversely. At standard AM, noise performance is actually what bad, always bad compared to our DSB-AC, right? So this is because of actually what wastage of transmitted power, right? In carrier is not suppressed. So wherever you need your aim only what simplicity of the system or transmitter and receiver, you can go for standard AM. But if you are particular about noise performance, you will have to go for DSB SC. So maybe it will be more clear, right? When I say it's bad compared to DSB SC, how bad it is. If you want to know that, maybe we'll have to solve a problem, right? So it can be a problem or it can be a derivation. So whatever, right? So maybe you can take it down, right? Show that figure of merit of single tone AM for 100% modulation, 100% modulation is 1/3, right? So this is what you have to show, right? So it can be as a derivation or as a proof, right? So this just to compare this. So why? Because the single tone AM, it is one of the what easiest case of standard AM, which where message signal is a single frequency or single tone signal or a sinusoid, right? M of t is a sinusoid. So we can just now we derived this equation of figure of merit, right? Ka square p by 1 plus Ka square p, where this p is nothing but what? Message power, right? So we can write figure of merit of standard AM, right, using envelope detector. It is Ka square p divided by 1 plus Ka square p, right? So where this p is nothing but what? Message power. P is message power. P is message power, right? And Ka is amplitude sensitivity, right? Ka is amplitude sensitivity. So K and P are given in this problem, but K and P are not directly given. So what is given is given in this problem, given percentage modulation is 100%, which means modulation index is equal to 1, right? Where this modulation index is nothing but what? Ka into AM, if you remember, right? Modulation index is nothing but what? Ka into AM, right? So and in single tone modulation, as it is mentioned, single tone AM, right? We can write M of t is AM cos 2 pi FMT, and we can always write M of t is AM cos 2 pi FMT. So what will be the power in this? Power of M of t, power of M of t, what will be this? Right, whoever gives the answer first, right, has got a reward. What is the power of? Shreyas is telling it is equal to 1, not correct. No, you have typed it early before, I think. Right, not, yeah. What is the power of? Yes, half of AM square. Shreyas, okay, yeah, okay. I understood it. You typed it in typed it some 6 minutes before, right? So Pritish, you have given the correct answer. That is half AM square. That is correct. It's a sinusoid with peak amplitude equal to AM, right? So the RMS value will be AM by root 2. So the square of that will be AM square by 2, right? So that is AM square by 2, AM square by 2 or half AM, right? That is correct. Now, what is the time domain expression of single tone modulation? It is a standard AM, right? It is AC into 1 plus Ka M of t cos 2 pi FCT, cos 2 pi FCT. But here, like this M of t is actually what? AC into 1 plus Ka M of t is AM cos 2 pi FMT, AM cos 2 pi fmt times cos 2 pi fct. This m of t is am cos 2 pi fmt cos 2 pi fct, right? With this ka into am, you know it is equal to mu. Ka into am is nothing but what? It is equal to mu, right? So we know that ka into am is mu, but okay, fine. So now what we'll do is we'll substitute the value of p in the expression of figure of merit, right? We'll just substitute and see that figure of merit or am, it is equal to ka square p divided by 1 plus ka square p, right? 1 plus ka square p. This is equal to ka square. P was nothing but what? Am square by 2. Ka square am square by 2 divided by 1 plus ka square am square by 2. Right. So now from this we can take half. It is half ka square am square divided by half times 2 plus ka square am square. So we can rearrange it like this. And you know ka am is equal to what? Mu. So ka square am square will be equal to mu square. Right. This half and half will get cancelled. Right. So this is equal to mu square divided by 2 plus mu square. So this is the same expression that we got for this percentage efficiency. Right. Figure of merit is same as that of percentage. Mu square by 2 plus mu square. Right. So this is the figure of merit. Now what we have is we have mu is equal to 1. So if you substitute mu equal to 1 in this, what we will get? We will get FOM of AM when mu equal to 1 is given by 1 by 2 plus 1, that is equal to 1 by 3. Right, so we are getting 1 by 3. So what we got now was figure of merit, that is SNR output by SNR channel of a standard AM system for 100% modulation is 1/3. Right, whereas if it was DSB-SE, the FOM was 1. But when all other parameters are kept constant, right, the figure of merit or noise performance of standard AM was only 1/3, which means if you have to achieve same noise performance as that of DSB-SE, that is, say when I say same noise performance means figure of merit equal to 1, you should transmit 3 times more power in AM. Right, you should transmit 3 times more power in AM so as to achieve the same figure of merit as that of DSB-SE. That is the that is what we can infer from this particular problem. Right. So this is what we had to prove. This is equal to 1 by 3. Right. So these figure of merit equations you can remember, or else you can derive it easily. It's not a big task, big deal. Right. But right, if you as and when you practice it, you will be remembering. So you remember, you will be right. So we know the figure of merit of DSB-SE is 1, and standard AM was like always less than 1, and that is actually what equal to k square p divided by 1 plus a square p. Right. So that will always be less than 1. Now we have to see what is the figure of merit of FM. But before that, right, while we did this particular derivation, while we evaluated the figure of merit of standard AM, right, what we did is, right, we have assumed this AC into 1 plus KA M of T is much larger compared to noise, right? The noise is negligible, right? That's what we have assumed, right? So that the angle between the resultant and the message, right, it was negligible, so that we could approximate y of t to be equal to what? The AC into 1 plus km of t plus ni of t. But if this is not the case, for low carrier to noise ratio, when I write CNR, that is actually what? Carrier to noise ratio, which means carrier power is much less compared to the noise. right? Or this entire term as such, AC into 1 plus K M of T, if it is much less compared to noise, so what happens is, right, this noise will be predominant, right? So noise, right, this is actually what Ni of T cos 2 pi FCT plus, sorry, minus NQ of T sine 2 pi FCT, right? Sine 2 pi FCT. This will be predominant, and this R AC into 1 plus K M of T. If I am representing it as phasor, right? Its magnitude will be less, and it may make some angle, say psi with this, right? It may make some angle, say psi with this, right? With this noise. Then the resultant, right? You can see the resultant in that case will be what, more comparable to noise, not to message signal, right? So in such cases, right, this envelope detector will not work reliably, right? I told initially itself, when I assumed y of t to be equal to what, AC plus AC km m of t plus in phase component, that assumption will hold good only when we have a very high carrier to noise ratio. So when we have very low carrier to noise ratio, what happens is there is something called threshold effect in envelope detection, right? There is something called threshold effect. So a threshold effect means whenever the carrier to noise ratio is less than a level, less than a threshold, right, the message signal will be lost, right? Or the envelope detector output will not have any message component, right? Will not have any component which is proportional to message, right? So the loss of message in an envelope detector, right, that operates at a very, very low CNR, right? That is actually called threshold effect. Right. That happens when noise, right, or CNR is much less compared to 1, or carrier power to noise power is much less compared to 1. We won't be able to reliable demodulation or detection is not possible. At that time, message will be lost, right? That is called thresholding effect. And this threshold effect, it's present in say only in non-linear demodulators, right? Non-linear type demodulators, like example is envelope detector, right? Like example is envelope detector. But in coherent detector, it is not present. In coherent detector, threshold effect is not right. So present. So when if someone asks what is threshold effect, when carrier to noise ratio is small compared to unity, the noise term dominates, and what happens is the performance of the envelope detector, like it changes completely. Um, it can't give reliable demodulation, right? So the loss of message in an envelope detector, right, that operates at a low channel to noise ratio, it is referred to as threshold effect, right? And it is present in envelope detectors. For this, what should that's why, maybe we are thinking carrier is unwanted, it doesn't carry any information as such. Maybe if you think, okay, we can reduce the carrier power abruptly, but it will affect the performance of the system, right? You can't use envelope detector. Then you will have to what, if you want to reduce the carrier power, or if you want to literally suppress the carrier power, then you should go for complicated systems, right? So that is a trade-off here between system complexity and the power, right? So that's actually what a threshold effect. So this threshold effect we will study even in FM receiver, right? In all non-linear demodulation systems, we have this threshold effect. Please do remember, whereas in coherent detector, we don't have the issue of threshold effect, right? So that's about AM Yeah, u square by 2 plus u square by 2. Yeah, okay. So that's about AM. Now, right, if you have any doubt, you may please ask. Otherwise, I'll randomly call anyone and ask to share your note, whatever you have taken down. Right, I'll take some 2 minutes extra. Mm, whom should I? If there is any volunteer who has taken down and have to save the entire class, can come forward. Otherwise, I'll only call someone. Maybe I will call. Yeah, people started leaving. So yeah, and anyone can come forward, right? So if I may ask, Satvik, Satvik,
Yes, sir.
yeah, have you taken down this derivation? Have you done this
Yes, sir.
derivation along with me?
Yes,
Yes,
sir.
yes. May I ask you to show that once?
Okay, sir.
Hmm? You can just switch on your camera and show it to everyone. Right? It's just I'm sorry, I can't see anything. Right? Huh? I can see a blank page.
It's there, sir. Notes. Can you see it,
Eh,
sir?
Anyone can see maybe right.
I'll zoom it, sir.
No,
Is it visible, sir?
anyone can see. Can anyone give me a feedback? Is it only me who can't see, or Shreyas? Very blur. So Shreyas, thank you for giving a feedback. Right. No,
Sir,
maybe
but
you
the
can.
camera.
You can. Huh? You can click. No, I'm not right. As I told, I should do this. Maybe you can click a pic and then share
Okay,
it with everyone. Please wait. I'll take hardly 2 more minutes. After that, I'll leave. And maybe all of you can click a pic now. Click a pic, and I may ask anyone to share. No, I'm just doing this to make sure like some learning is happening. Right. Otherwise, these things, even though it sounds simple, but there are some aspects behind each line of this derivation which you may not be able to uh, like remember, or you may not be able to appreciate at a later time when you're trying to study on your own. For instance, right, the phasor, right, being approximated to the real part of it. Right, normally we never used to do that, right? But we have done this, but with some justification. So those things, right? When even if you're trying to right read it at a later moment, at times you may find it confusing, and that's why I'm insisting everyone to what like these topics that anyhow at least for the attendance sake all are attending the class, right? So you can learn here itself. Yeah, I hope all of you, all I have requested all of you to what click a pic of your note. Right now, if I may ask Shifani, can you please uh, click and share your screen.
Sir, I'll show it right away.
Yeah, okay, please. Yes, at least, yeah. Something is there. This is, yeah, visible. Okay, fine. Thank you. Right. Like it's not to what. Please don't feel bad. Right. I just wanted to make sure all of you are doing it along with me. Right. If someone has not done, right, please do it. Yeah. So that's it. Maybe thank you so much for joining. If you have any doubt, you can ask. Otherwise, you can leave. Right. Maybe we'll end as Shrisha told. We'll end the class with a prayer. Right. Why was that told, Shrisha? National anthem. Not now. Yeah. Thank you. Thank you so much for joining. Yeah.